let's move on to the next talk. As you see, there really is quite a variety of different presentations. And this next one is certainly going to be something very different again. This is a talk by George Hathaway. And George Hathaway has a very interesting background. He is an electrical engineer from the University of Toronto. He's worked in a lot of different areas, material science, pulsed power, quantum optics, energy and propulsion, and with a lot of different people. He is really the Indiana Jones of new energy research, in the sense that he's this swashbuckler who's gone around testing different sorts of energy technologies from all sorts of places. He's one of the most fascinating people I know. You can sit and talk for hours and he'll never repeat what he's told you before about his energy research. Today, he's going to be telling us a little bit about that. The title of his talk is Fundamental Issues in Energy Harvesting. So, George?
Thank you. Let me share my screen. Everyone hear me, I presume? I hope so. Okay. Let's see, where is it? All right. Well, welcome members of the Anti-Eddington League. I appreciate the once again the honor to be amongst all these forward thinkers and folk who have been able to overcome their junior college or university concerns about second law and first law violations, and hoping to proceed into the next realm of I guess it's number 4 in Daniel's chart of historical movement towards something that will help us as a species, which we sorely need. And as Jim Jaschewski had talked about earlier, hopefully prevent what he calls a dragon king scenario. And if we can convert some of these ideas into something that is widespread, widely available, and at reasonable cost, and can be installed as commercial devices, then we are many steps along that road. And as I mentioned in a previous talk, my goal is to offer my services at Hathaway Research as sort of a go-between or bridge between the inventions that we're seeing now at this conference and in others, and the commercial realm. And so I've been concentrating a lot in my past work on looking at rather large-scale effects. As I had mentioned earlier, the issue with a lot of investors is, can I see something that I can put on a table, or can I build a plant with, or even make something as I had asked for, discussed in a previous talk. Can we make a coffee pot size something and have airflow through it, and maybe a catalytic converter of the type that Daniel has talked about, and have a couple of wires out and power your microwave or your perhaps your house. Anyway, those are the kinds of things that I have been examining over quite a long time. And Garrett was kind enough and maybe bold enough to ask me whether I could talk about a few of the kinds of things that I've been investigating many of which you might know already from a thermodynamic standpoint, some of which will be clearly capable of analysis thermodynamically and some not. And I will end the talk, as I usually do, if I have time, to take a look at some of the pitfalls and problems in the measurement of the kinds of systems that I've come across in the past. So we've all gone through in great and delicious detail on this conference, and especially today, the thermodynamic laws, number 1 and 2 in particular, and I don't think I need to dwell on any of these at any great length. The conservation of energy is generally the one that I have been asked to pontificate, you might say, on for both investors and inventors who claim that a system that they have worked on generates energy from nothing. Less activity has been expended on the entropy end of things, namely the second law, the spontaneous heat flow law. Anyway, be that as it may, we've gone through the various easy types of analysis, and I think it was Daniel who mentioned that he had come across, 21 different formulations of thermodynamic laws, perhaps the second law only, which is quite amazing. From the engineering standpoint, we have steam engine type of work producers using the difference in heat between, or difference in temperature, I should say, between a hot reservoir and a cold. And we also have refrigeration types. As you can see, I'm looking at this from an engineering standpoint, where we can extract energy from a cold reservoir and dump it into a hot reservoir. One thing that I haven't noticed in the discussions so far is whether any analysis has been done or consideration thought given to not only increasing, say, the heat or heat flow to a hot reservoir, but removing heat from a reservoir. All of the systems that we've been talking about, or as far as I can recall, talk about increasing heat or heat flow from the hot reservoir back to the hot reservoir. And I'd be interested to find out whether there are any ways of removing heat spontaneously from a bath. And given the fact that a lot of folk are concerned about global warming, maybe if we could determine that there's a way of treating the cold bath as a way of or as a reservoir that can be pumped into, namely or cold or heat removed from it, that would be an interesting different approach. So I think it was Daniel also who mentioned the two main second law statements, the Kelvin-Planck, and I call it reverse steam engine statement. And I bring this up as this quote saying it's impossible to make a cyclic device which receives heat from a hot reservoir and produces work. What is interesting to me is the word cyclic and the comparison between cyclic and spontaneous, which is a sort of a metaphysical distinction that I've been wrestling with, which comes up in the Clausius, and I call it the reverse refrigeration statement. Namely, it is impossible to make a cyclic device, which spontaneously, and you got those two words together, without external work transfers heat from a cold body to a hot body. It's, according to Clausius, that's not the case. However, it was shown, I can't remember if it was Boltzmann or who it was that showed that these two statements are actually equivalent, and they constitute what was considered an ironclad, at least to Eddington's view, and others' view that there's no way we're going to circumvent either the first or the second law. However, I also have a question comes up with regard to how we define heat and heat in the context of these statements. Do they apply to systems, as I say at the bottom here, where heat is defined also to include random electromagnetic or EM-like fluctuations, for example, zero-point fluctuations? So I bring that up also reminding us that Tom Vallone initiated that, I think, that idea that perhaps some of our system boundaries should include a consideration of zero-point fluctuations, as I believe will be exemplified with Garrett's presentation after mine, which I hope I'll leave lots of time for. Or something like, if you know anything about low energy nuclear reactions, you probably have come across the so-called Widom-Larsen theory, which requires these magic surface plasma oscillations to suddenly bubble up into a larger or a much higher energy state, which allows the conversion of nucleons to neutrons and stimulates the low energy nuclear reactions in their view. Would that also be considered heat? And there are a number of other areas that where the definition of heat in thermodynamic terms is rather fluid, you might say, and it's hard to pin down. And that usually allows an escape route for folk who claim that they are violating or are adjusting the thermodynamics of their system because they are saying, well, we're not inducing heat. We're not worried about heat. We're talking about surface plasma oscillations or something like that. So interesting definitional issues from time to time. I've shared these screens before in terms of excitement and overexcitement, and I'll zip through them. Here's, for those who haven't seen it, my daughter building something up from bits and pieces, or helping to build stuff up from an assembly of components into a unified whole, which you might consider as neg entropy or reverse entropy. And here's what happens when there's too much stimulation. Things just tend to flatten out into a lower energy state after a day of hard work at the lab. So let's take a look at some of thermodynamic issues with regard to the ability to measure these things, at least at the scale that I've been involved with. And as I say here, generally, which I've been mostly involved with first law, although this is a conference, today's mostly second law issues, but I will concentrate a little bit on first law because it's usually the most relevant at what I call macro, or which is the cosmic scale, or meso, which is, say, the lab scale devices that I've been involved with mostly. And in these kinds of systems, the boundaries, which are extremely important to take into account, are much more easily defined in general, I should say, and therefore more straightforward to measure and determine the validity of the devices that are claiming to have circumvented or completely negated the first law. The second law is more relevant in my understanding and in my experience to more microscale and nanoscale energy interactions, as we've been talking about, Professor Lee talking about protons involved in ATP activity and for instance, some of the chemical reactions at catalytic surfaces, as Daniel Sheehan has been talking about. I call these microscale, and they're generally more difficult in terms of measurement to set the system boundaries and measure. And as Garrett has asked just a few moments ago in Professor Lee's biological discussions, are there any other reactions that could take place that might contribute to the heat that the T term, the environmental term, perhaps, that would cause the PMF to be as high as it is? And I'm sure Professor Lee has looked at all of these, and as his answer clearly showed, but it certainly is required to think outside the constraints of the system that you're looking at to see what other flows of energy may need to be accounted for, which is fairly obvious, but I'll state it anyway. Typically, as I say, thermodynamic law violations in my understanding and the kinds of work that I've been doing result from several things, most prevalent being faulty or incomplete measurements. And I will come back to that at the end of the talk when I go through my endless lists of pitfalls and concerns about how to measure systems, especially in this case, energetic systems, whereas my last talk yesterday was more in force and gravitational or force measurement systems and measurements. In this case, I'm talking about primarily energy and power measurements. And this is usually, actually 90% of the claims that come my way can be put to rest by pointing out the inconsistencies or the incomplete measurements or the incorrect application of measuring instruments to the task at hand. Of course, as I say, I'm working more at the lab scale. The other kinds of measurements that we've seen in over previous days, including, say, atomic force microscopy and very tiny thermocouples and things of that nature. Most of the folk on this at this conference are pretty well versed in the kinds of pitfalls and concerns that might show themselves to produce prosaic explanations for what they're seeing. But in general, the kinds of devices that have come my way have not had that kind of very precise analysis of the measurements required to verify the claims. Also, incorrect system boundary definitions has been a great plague, as was emphasized before. God likes the crystals, the devil likes the devil's in the interstices of the intersection between the steady state, you might say, and without making sure that you have well-defined system boundaries, it's difficult to make solid predictions about the time progress of a particular system or the steady state claims. And of course, there's the energy inputs and outputs have they been consistently analyzed and accounted for? And a lot of times it turns out in the work that I've done, inventors say, well, the previous version of this device that I've improved on was shown to work, therefore mine must work. So I'm always concerned about an inventor's reliance on earlier versions of their device, and that happens with alarming regularity. You can see any number of these kinds of things on the internet. These energy claims. So some of the micro scale energy concepts, which I'll bring up, I'm only going to bring up two. One that hasn't been discussed at all in this conference is the idea of Loschmidt in the 19th century. I'll get into that in a bit, and then I'll take a look at Wyndham Larson in a tiny bit of detail as well, as a theory for the claimed energy production from low energy nuclear reactions, or as it's colloquially known, cold fusion. And Loschmidt here, for those who aren't familiar with it, hypothesized, as you can read, that a simple column of gas in a gravitational field. So, for instance, a column in a cylinder of gas, like can be any kind of gas, that you can apply, in Loschmidt's case, a kinetic theory of gas too, which is not the case, but a gas that doesn't react with any other gases, monoatomic or diatomic, but a single gas in a gravitational field spontaneously becomes hotter at the bottom. Well, how could that possibly be? Well, he reasoned, as I say here, that any collision between molecules in that column, and a lot of those collisions would be vertically or almost vertically, would on average send one molecule upwards, but as it goes up, it loses speed, whereas those going downwards, resulting from the collision, would gain speed. And using the kinetic theory of gases, those at the bottom would therefore be vibrating more quickly and be, by definition, hotter than those gas molecules at the top of the column. So you could manage to construct a simple heat engine, such as this one, from the Loschmidt idea. And this, to me, the Loschmidt idea was an example of the simplest that I had come across before this conference, questioning of the thermodynamic laws. And this is a typical picture of Loschmidt's device. There it is, the column of gas with the dots in it. And usually most analysis, as I mentioned down at the bottom, omit the environmental temperature, the delta Q there, going into the column. They only consider gravity as the quote driving force, and you can see that the heat flows in the column basically, or the differential in heat is between the cold molecules becoming hotter at the bottom, and if you connect the bottom to the top using a heat engine, you could theoretically produce heat from something. What is that something? If the environmental temperature is removed, you put it in a very well insulated container, this bottle of, or this column of gas. The only other force, you might say, acting on this is gravity. Is this a gravitational heat engine? Well, it's a question that has vexed a number of people. For example, Boltzmann considered it, as I said, an intriguing idea, but incorrect, using velocity reversal and time reversal considerations, especially of mechanical processes, and nowadays the question of the validity of the kinetic theory of gas brings into question Loschmidt's ideas. It's interesting that Boltzmann brought in time asymmetry to argue against a claimed violation. One thing I haven't seen or heard in this in the conference is at least in today's activity has been the influence of time. And I brought that up with regard to the second law. I mean, an explanation or an explication of time symmetry or time asymmetry in some of these systems, whether that would go towards questioning the validity of applying thermodynamic considerations to some of these ideas, such as have been talked about by Paul Thibodeau's and others. And another argument against Loschmidt, there have been quite a few, have been to do with velocity distributions and cutoffs and things like that. There are all sorts of them that have suggested, well, Loschmidt's out to lunch. There's no possible way that a gravitational field, being a conservative field, therefore can do no work. How could it do work on the system? Then another question is, if this is the case, is gravity actually producing a neg entropy state, a more ordered state, in providing work, which is a more ordered state out than this ensemble of gas molecules? Well, oddly enough, back in 2002, someone published a paper saying, well, in fact, I've measured a temperature gradient using a Loschmidt type of assembly of a column of gas and in a well-insulated container. So it's interesting that someone's actually gone ahead and measured that. I haven't looked into the details of it that much, but to first order, it looks like a reasonable experiment. Then I ask whether there's any relationship between Loschmidt's idea and what you're going to hear from Garrett. And I bring up this conservative nature of a force acting on an ensemble of moving particles, for instance. And can gravity do, as a conservative force, do any, as I say, sustained work on a system? But maybe can gravity act in the Loschmidt case as an asymmetric Maxwell demons? And we've heard from previous speakers on the requirement for asymmetry in a number of these systems that apparently that violate one or two of the laws. And can, in the Loschmidt case, or a generalization of Loschmidt, use gravity as I say, segregating particle velocities and thus allowing a heat engine? I have my doubts, but it's a question. Compare that to what Garrett will be talking about, is asking whether, in fact, 0-point fluctuations can be considered a conservative force and therefore the lowest energy state, but the addition of an asymmetry, as you'll see, the Casimir cavity on one side of his device, therefore making it asymmetrical, provides the needed asymmetry to segregate zero-point energy flow, you might say. So there may be an interesting correlation between those two ideas, resulting in perhaps a deeper understanding of what's going on in some of these areas. I'll go to LENR now, let's see, to just do a specific example of how folk have been concerned about how any kind of nuclear reactions at room temperatures could possibly take place. And I reminded of Heisinger's reality requirements for low energy nuclear reactions to take place. First and foremost, obviously, is how the Coulomb barrier could be possibly circumvented by having these the protons, for instance, in one view of LENR, overcome the Coulomb barrier between them and produce other particles like neutrons. And if there are neutrons being produced, where are the neutron emissions in virtually all of the cold fusion results, as well as gamma or X-rays as a result of these so-called or claimed fusion processes? Well, two guys, Whittam and Larson, put together a theory that attempted to answer all these criticisms. By the way, there are other theories that tried to answer these three criticisms. What I'm going to concentrate on very briefly on Whittam and Larson, only to bring up the idea that they considered that, as you see in the next one of their papers, and I don't know whether you can see my pointer here, but it was shown that collective plasma oscillations on the surface of, say, a palladium piece of metal contribute some of their electric energy to an electron so that the following reactions become kinematically allowed. So the idea here was that by some stochastic miracle, I guess, surface plasma oscillations, which were really not well defined, could combine, would nudge electrons to combine with protons and produce the neutrons. Unfortunately, there's never been a reasonable thermodynamic analysis that I've seen of Whittam and Larson. My own take is that there's an entropic problem here with what is how a spontaneously disorganized state, namely stochastically variability in a background state of oscillations, can suddenly combine, perhaps like a rogue wave, as Jim Jepcheski talked about earlier, into an energy state that is high enough to propel electrons into protons and produce the necessary neutrons. I'm finding that rather difficult to understand, at least. And my question is, does Whittam-Larson theory therefore violate at least the Kelvin-Planck view? However, there's been no definitive verification of low energy nuclear reaction claims. And I'll now come out of theory a little bit and look at experiments or commercial products after decades. Like Pons and Fleischmann are in 1989. What have we seen since? We've seen pronouncements that, oh, we've got something. Yes, the Spawar and others have at Navy have seen obvious traces of neutrons, therefore verifying this possibility that thermodynamics begone we've got low energy. We've got nuclear reactions from a low energy source, like ambient heat from in a low energy nuclear reaction experiment. And the latest thing was the Navy attempted to revive interest that I mentioned in 2019 without much success. In my opinion, the most advanced experimental capability for determining heat transfer is what is colloquially known as the mother of all calorimeters, or MOAC, which was developed at Hal Puthoff's Institute of Advanced Studies around 2004-2005 by Scott Little, their resident engineer and thermodynamicist. And there's a diagram that you can see of the complexity of this device, which was specifically designed for looking at the validity and testing the validity of low energy nuclear reactions. And you can see some of the features on the right. One I'd like to point out is the third point there, the size, shape, and I say shape, temperature, and location within the chamber. You can see the heat exchanger, the calibration heater in the center. That's the cell is sort of on the right of the center, right here. Just as an interesting point, a lot of calorimeters have been developed to show apparently energy gains in low energy nuclear reactions. But when you move the cell, or you move the sample that you're dousing with hydrogen from one place to another in the calorimeter, you get different readings. This is one of the only calorimeters where it doesn't matter where you put the sample with respect to thermocouples and conduction gas, and has very little effect on the measurements. And Scott has looked at a bunch of different kinds of energy devices to show to at least 0.1% relative accuracy. There's no excess heat in these devices. Here are a couple of photos of it. You can see the size of it relative to the lab. And there's the main chamber inside that white box. It's actively thermal insulated, so it's got active thermal insulation, whereas most other calorimeters are passively insulated. And there's a test cell inside that test chamber. So here's some examples, and those I'd call the low energy nuclear reactions an example of microscale energy activity or concepts and inventions. There are tons of lab scale concepts, many of which I've had the fortune or misfortune of examining, which have issues, you might say, with thermodynamic laws. Randy Mills' brilliant light or hydrino device is one example I will show presently. I talked about Peter Granot's underwater arc explosions in a previous talk yesterday. As for fun, I'll bring up a couple of others that have to do with solid state, you might say, no moving parts, energy generation from nothing, basically, and then a rotary device, actually from Canada, in the short time. Let's see, how are we doing? Yep. Here's an announcement from the most recent version of Mills' brilliant light power. If you haven't seen it already, it started as Mills is a doctor, a medical, an MD who's published a work that shows the masses, was able to derive the masses of the fundamental particles in several papers, which actually were pretty well received and peer reviewed. Based on that understanding, he developed what he called a low energy state of hydrogen. And this low energy state of hydrogen he called the hydrino. And this was years and years ago. He started this this path, and as you can see from this, if you can read it, from a very humble beginning of describing the development, the possibility of hydrinos, we come up to dark matter and unified matter and harnessing catalytically this dark matter directly into an energy device called the hydrino, brilliant high energy light. Wow, look at all this, it's amazing. And with this simple idea, he has gone on to attract quite a following, as well as a lot of money to develop some of his original ideas into what he claims is an energy production device. The basis of his claim is shown in the in this white box on the right, and basically somehow atomic hydrogen reacts with a catalyst, and by some means energy is transferred from atomic hydrogen to the catalyst, which forms an ion itself. And this is, by the way, directly from his an early website on what a hydrino is. And the negative, at least he's very kind enough to remind us that an electron is a negative entity, drops to a lower shell, squeezes down closer to the proton. Thank you for telling us positive, to form a reduced size hydrogen atom called hydrino. Now, there's already thermodynamic concern here about what is understood as the lowest energy state, and whether it's possible to actually reduce an entity to a state with lower energy than the lowest energy the lowest energy state. And I question, of course, this claim that by doing that, you release energy in the form of heat, which then can be used to operate machinery and things like that. And then there's a cycling. This number 3 is cycling this whole thing back again, but with not only is the thermodynamics, you might say, of going from a hydrogen atom to a lower energy state than the lowest energy state a problem, but then he says, now if you add a lot of electricity by means of ionized or by an electric arc, then the space charge around these ionized electrons is eliminated, and this process, this reaction, so-called, becomes massively high. And I ask a couple of questions based on this. And just a reminder that Mill's atomic theory is based on classical rather than quantum mechanics, and it's been criticized roundly by various people, including Rathke in 2005. Anyway, I'm not going to go through this, but in any detail. But some of Mill's supporters claim that they have done their own tests on this and have come up with a confirmation of what Mills was saying. However, I brought up at least 14 points against or questions on one of these papers to try to satisfy, to my understanding, how well or not well these analyses have been done, and they've, in my opinion, not been well done. Anyway, here's the most recent version of Mill's device, where you have these big electrodes in here. You have the hydrino formation on the catalyst in this chamber, and when you apply a very high voltage from capacitors to this, the electrodes in here, a huge explosion takes place, sending a column of conducting material, in this case liquid silver, through this MHD generator and cycling back and forth. And he claims that by means of the production of hydrinos in here, he can get excess energy well above the energy required to drive the whole system, including capacitors to make the arcs and the pumps to pump the silver in and stuff like that. Anyway, here's the most recent version of it, and it's attracted a lot of attention, and but no one seems to have done much analysis on the input energy side, which is the most difficult, namely the formation of arcs. I will go and skip over Peter Grenot's work, which I talked about yesterday. That's Peter Grenot in the bottom right, and that's a junior version of me. And we're looking at one of his water fog experiments, where he claimed that the kinetic energy produced by underwater electric explosions is greater than the energy required to provide the arc, namely to charge the capacitors, which are then discharged to provide an arc underwater. And as I mentioned yesterday, I published a couple of papers with Peter attempting to show that this was an energy producing device. It wasn't in violation, actually, of first law, because we determined that the energy came from the sun in a particular cyclic manner. But upon analyzing exactly what what was going on in the arc, I determined that the energetics were not as we had originally claimed. I had to retract that. Anyway, that was a discussion of Peter Grenot's activity. Then we come to a typical example that you'll find on the internet of a system that claims to produce energy from permanent magnets. In this case, there's a permanent magnet here and a couple of coils in a circular loop, and little coils that are here change the flux from a permanent magnet from one side to the other, from one side of a yoke to the other, through these pickup coils. And the claim is that the energy output from these pickup coils is greater than the energy required to deflect the flux. This claim, Tom Bearden wasn't the first to develop this kind of device, but he's the most famous. And as I say, the alternating flux generates a current in coils. Claim was that the power used by the switching coils was less than the power output, in clear violation of first law. And the proponents claimed that the permanent magnet actually was a source of power, which slowly degrades over time. That's how they got around claims or concerns that they're violating first law. And a permanent magnet, of course, is not a source of power. It produces a conservative field, you might say, and it only degrades negligibly over time. Anyway, from the semi-sublime to the ridiculous, here's a rotary device which claims to violate Lenz's law. And we haven't talked about first law systems in a rotating configuration. But here's an example of someone who claims to be skirting Lenz's law. Here are permanent little disc permanent magnets on this rotor driven by this motor, and they come across and close to these pickup coils. And the claim is that you can reduce the power driving the drive motor if you get to the right relationship between speed and magnetic flux, and therefore you can circumvent Lenz's law. And this is the inventor here, a Canadian fellow near Ottawa, Ontario, who claims that he can produce excess energy essentially by skirting Lenz's law. And he interprets he shows that the motor speed up can occur when his motor generator system is at a particular apparently low energy state, and therefore he can gain energy from this speed up, which is not the case. No increase in power, violation of the first law. An induction motor, he just forgot that can operate in a range where torque actually decreases with speed. And anyway, we will end this part with the consideration of Lenz's law as a magnetic version of the first law, and states that when a magnetic flux is increased through a closed loop, a current is induced that opposes the force. And if there's no opposition, no work can be performed. And this is exemplified if there's no Lenz or Newtonian back reaction. The source of flux can change however it wants, but the coil does not absorb any energy of motion. So a lot of systems that I've investigated claim to have subverted Lenz's law, but which is a version of the first law, but clearly they don't. I can get into, in the last couple of minutes, the issues surrounding measurement, at least of the kinds of systems that I've been involved with, and why we need to measure. Look, taking a step back, we need to highlight, as I say, which measurement issues factor into the evaluation of uncertainty. It really is an approach to minimizing uncertainty that we're all trying to get to in doing experiments of this kind. And most of the properties are quantitative in nature, and they resolve themselves eventually into a decision, at least at my end of things, where I'm trying to convince investors to help fund or be interested in particular areas of energy research. They have to make a decision, and they have to make a decision on the basis of a comfort level in measuring the claims. And what I need to do is to reduce the uncertainty in the kinds of measurements that I'm doing for both investors and inventors. And also, unless the methodology and results of a measurement can be transferred comprehensively, in other words, can I describe to you the results of a measurement in terms that are comprehensible to you, it won't make much of a difference. And the lessons I've learned, some of them, consider all relevant explanations to a particular problem. And we've heard lots of those in the conference so far. Did you think of this? And what about that? And please give some thought to this possibility. And is it possible to design the simplest measurements and the simplest system that will validate or not the claims that are being made? Don't keep adding more components and more complications because, oh, we better check on this, better check on that. Let's design the simplest system, look at the boundary conditions, and make our decisions, measurement decisions based on that. Also ensure that sufficient information is available. Make sure you look at the history of the kinds of things you've been doing, so that you can learn from what other mistakes others have made, and always beware of confirmation bias. Be concerned when you think, gee, I got a measurement, sorry, I have a theory, and the theory predicts that this is going to happen. I set up an experiment and I see this happen, therefore my theory is correct. You got to be really careful of falling into confirmation bias, logical problems, and concentration obviously on claims backed up with a reasonable theory. Let me see how we're doing. I better stop fairly soon. I will direct people's attention, if they wish, to the second half of my nightmares in the art of measuring, or as I say, what could possibly go wrong, Chief? Yesterday I talked about the issues, or some of the issues that befall experimentalists in looking at forces. And I have this part of the presentation, should I have the time, that examines issues in electrical power and energy, electromagnetic effects, etc. You can see all this as well. And as an example of the density of some of these issues, here are just some issues that I've come across, just encapsulated a couple of phrases for looking at electrical energy and power measurements, and the division of frequency. I do it by division of frequency, and power in rotating systems, what you have to be careful of, Faraday cage issues, which are not very well understood by a lot of people, at least those who have built cages or enclosures and found, oh my God, it doesn't work the way I expected. There's a leakage here. How come? I thought I'd just have to throw a bunch of copper together and everything would be fine. That's not the case. Anyway, lots of other issues that we can talk about offline if you wish, or you can email me. I can send you this, or it'll be, these kinds of things will be available in some kind of form or another once SSE gets a hold of it. So you can see there's quite a bit of quite a number of issues that need to be taken care of before reasonable analyses can be done. Thank you very much.
Thank you. Thank you very much, George. This, you've painted a broad canvas here, and there's a lot for us to talk about. Unfortunately, there's no time for questions because we've run up to the full hour. And so there will be some discussion that we can have in about an hour.
Yes, that's fine. Thank you.
Discussion. So let's take a 1-minute break and then we'll start the next session.
Can I ask George about Podkleidenhoff?
Let's hold off for an hour, okay?
All right. Reluctantly, I will.